Hey, good morning, everybody. All right. All right. Um, welcome to our last day of class. Um, hey, I've enjoyed the semester. I always enjoy these ITV classes, even though they're a little bit different than a standard format. But I like teaching them. They're fun to do. They're fun to. it's It's different, but it's also always cool when I get to meet y'all out in the real world. There's been about 3 times this semester where I've had a student from previous courses, whether I run into him at SPC or I run into him somewhere in Lubbock, and they'll always say, "Hey, you were my um, algebra teacher." In ITV computer class. So it's always cool to get to run into y'all in the real world. All right. Anyways, I've enjoyed the semester. Let's get talking about the review. Again, let's address questions that you have in terms of the review or exams or anything that you want to go over. The floor is yours.
Can we go over number 68 on the review?
58 on the review, certainly.
68.
68, okay. Okay, problem 68. We want to find the inverse of f of x is equal to a 3x minus 4. Okay, um, so I'm going to write this out. You can always go back and review, but here are the steps. The first step is to replace that f of x notation with y. That's the first step. So we're going to rewrite this as y is equal to 3x minus 4. Then the second step is to now solve, or excuse me, not solve, but swap x and y. So this is where that swapping comes into play. So now this becomes x is equal to 3y minus 4. And then your third step is to now solve for y. You want to get y by itself. All right, so let's talk about y. We have 3 times y minus 4. To get y by itself, we'll start off by adding the 4 to both sides. So we have x plus 4 is equal to 3y. And then to get the y by itself, we'll just divide both sides by 3. So we have x plus 4 over 3 is equal to y. Or you could write it as y is equal to x plus 4 all over 3. And then the fourth step is take y and replace it with the inverse notation, f inverse of x. So we have f inverse of x is equal to x plus 4 over 3. And there is our final answer. Okay, so I want to do 2 things with this real quickly. Um, Number one, let's do a little quick check. Now, this little quick check isn't a way to prove that these are inverses, but it's a pretty good way to um, guarantee that you got it right. So let's pick, let's let x be equal to, it doesn't matter what you pick, let's let x be equal to 4. So f at 4, the f was the 3x minus 4, so that becomes 3 times 4 minus 4. 12 minus 4, that's going to be 8. F at 4 is equal to 8. Now, here's the idea between inverses. You take an input and an output for a function. If you swap those inputs and outputs into this other function, then you're still going to get a true statement. So the idea is then, let's do f inverse at not 4, but 8. Now f inverse is going to be the 8 plus 4 all over 3. So 8 plus 4 is 12 over 3, and that becomes 4. So do you see this inverse idea? The idea here is that your input that you plug in up here becomes the output, and the output that you have here becomes the input. That's a quick way to verify that, hey, these are indeed inverse functions. Now this is just a quick way to check. I want to take a moment here to just talk about how do we prove. So this is a check. How do we prove that these are inverses? Well, we got to show that f of f inverse of x is equal to x. And we have to show that f inverse of f of x, what happened there? F inverse of f of x is also equal to x. So this is by composition of functions. So what we're going to do is we're going to plug in, to start here, we're going to plug in f inverse into the function f. So f is 3x minus 4, so I'm going to replace this x with my expression for f inverse. That's going to become 3 times the x plus 4 all over 3 minus 4. Look what happens. The 3's cancel out. You're left with x plus 4 minus 4. The 4's cancel each other out, and you're left with x. Exactly what we set out to prove. You're left with x. Then we do the same thing, but what we're going to do here is we're going to start with the inverse function, and we're going to plug in f of x. So inverse function is x plus 4 over 3. We're going to replace that x with 3x minus 4. So we have 3x minus 4 plus 4 all over 3. Alright, here, the 4's cancel out, leaving us with 3x over 3. The 3's cancel out, leaving us with x. So, this is how you prove that two functions are inverses of each other. If you do the composition, plug one into the other and the other into the other one, and you get x, then you know that they're inverse functions. This is a quick way to check. It doesn't, this is just a nice little check. You can say, all right, I think I got the right answer. But if I say to prove that two functions are inverses of each other, then you got to go through this process. All right, cool. Does that make sense? We good with that one?
Yes, sir. Thank you.
You're welcome. What else can we look at?
Can we do number 70?
Yes. Alright, so as I read 70, find the accumulated value. So, of an investment at 5.25% compounded continuously for 7 years. Alright, so the formula that we are going to use here is A is equal to P times 1 plus R over N raised to the NT. I've been talking reviews for so much the past few days, I forget what I've said. This will be on your formula sheet. You're going to have exam 2. If you go back and look at exam 2, there is a formula sheet at the end of the exam. Had a bunch of formulas that we utilized in unit 2. You're going to have a formula sheet. There's going to be some added formulas to that because we've looked at some things since then. I might have added some other thoughts. And just like in exam 2, I'm going to give you the formula, but I'm not going to tell you how or when to use it. That's your job to figure out what do I need to use a formula for this problem, and which formula do I use? Well, you're going to have a mixed bag of formulas. So this formula will be provided to you along with the formula for problem number 69. 469. So I got this mixed up. You said problem number 70, but I was looking at problem number 69. So I'll make a quick correction. If you've already done 69, this is the formula for 69. Why is this the formula for 69? Because in 69 it has this phrase, compounded monthly. That's why we use this formula. So let me just highlight that. Compounded monthly means we need to use this formula right here. You asked about problem number 70. Now 70 says compounded continuously. They put one too many I's in there. This is why I'm a math teacher, not a English teacher. The formula here is A is going to be equal to PE to the RT. Again, you will have this formula and that formula will be on the formula sheet. So, compounded continuously means we need to use the continuous compound interest formula. So now it's just a matter of plugging in the correct values. Find the accumulated value. So that means we need to find A given the following. We have an investment of $3,000. So that means that P is equal to the 3,000 at a rate of 5.25%. So R is going to be equal to a 0.0525. Always, always, always write your rates in the decimal form. Convert that percentage into a decimal form when you're doing any sort of calculations. Compounded continuously for 7 years, so T is going to be equal to 7. So in your calculator, you're going to do the following. 3,000, open parentheses, or actually you don't even have open parentheses here, E, raised to the, now my calculator, when I do E, it puts my little housetop notation, opens up a set of parentheses. And in my set of parentheses, I'm going to do the 0.0525 times 7 close my parentheses, and hit enter. And that should give you the 4,332.36. Some calculators, when you do E, what they do is they bring you up into this little, they have this little box up there. And this is where we would input all of this. So if your calculator does this, make sure that that 0.525 times 7 is all up there in the exponential position. Make sure all of this is in the exponential position, because if the common mistake that I see is in our calculation, somehow we get out of the exponential and we put this 7, outside of, we put the times 7 after we do this. And that throws our calculation way off. So, hopefully you can follow either of these two examples for how to do problem number 70. Does that help?
Yes, thank you.
You're welcome.
Mr. Clopton, how many questions are there on this exam?
So I went through, was it Wednesday or Tuesday? I can't remember. I was going through the exam, just looking at it. I'm going to go through it one more time today. And at this point, there are 32 questions. 32 questions. And there's a selection of bonus questions. So let me just go ahead and talk about this. There's 32 or 33 questions. I'm going to look through it one more time today. I don't really intend on adding anything, because right now the number of points total up to 100. Most of the questions are worth 3 points. There are a few questions in there that are, there's like 2 that are worth 5 points and a few of them that are worth 2 points. So most of the questions are worth 3 points. Again, there's some bonus problems. So while I'm just talking about this, here's my thoughts for the exam. Some of you are just going to go straight through the exam. 1, 2, 3, 4, 5, 6, so forth and so forth. Some of you may find that you like to move around, and so that's fine too. You're going to have the space on the exam to do your work just like all the other exams. I will have a scratch paper area for you to do scratch work on. If you utilize that scratch work, please indicate in the problem that you're working on. So if you're working on problem number 5 and you got to use scratch paper for it, in the space for problem number 5, say work is on scratch paper. Because if I don't see that, and I'm not going to go and look for the work, you have to say work is on scratch paper, because I'm not going to go and look for it. So if there's no work, you're not going to get any credit for that problem. But what I was going to say is, you had the full 2 hours for the exam. So I've been mentioning this 2 hours for a while now. And I've been talking with the facilitators, and things are being arranged so that y'all have that full 2-hour time slot. It needs to be done in one sitting. We're not breaking it up like we did the other exams. But don't spend, a whole lot of time on one problem. If you're sitting on one problem and you're just kind of trying to figure it out and you're not really getting anywhere, just move on. Go find something else to work on. And if oftentimes I find that as I'm working on something else, I'm just like, oh, that reminds me, I know how to do that problem now. And so don't spend too much time working on one problem. So like I said, 33 or so questions. Most of them worth around 3 points each. And there are going to be some bonus opportunities. Follow the instructions. I can't emphasize this enough. Make sure to show full and complete work. Most of these problems require some form of work, some sort of computational work. Make sure that you are showing your work. No work means no credit. So if I just see an answer written down for most of these problems, I'm just going to mark it wrong. If there's no work, wrong. Show me the work. Now, some of these problems, there may be a problem or two in there that's just like, oh, look at the graph, answer it. So I recognize what problems require work and what problems don't. I don't know if there's anything else. I could probably keep on talking about my thoughts about the exam, but I'd rather, does that answer your question? You satisfied with that answer? 33 questions?
Yes, sir. Thank you.
Alright. Alright, what else can we look at?
Can you do number 46?
46. Sure. Okay. So what we have right here is we have a quadratic function. We know it's quadratic because x squared is the highest degree of the variable x. So question number A, does it open up or down? Well, so let me just do something really quickly before I do this. What we want to do is we want to compare to ax squared plus bx plus c. Okay. Alright, A. Does the graph open up or down? So this is stuff that you just got to know. If A is greater than 0, then the parabola opens upwards. And if A is less than 0, then the parabola opens downwards. So, since for us, A is equal to -1, which is less than 0, that means that the parabola opens downwards. Opens down. So, gotta know that. B. What is the vertex? So the vertex form of a quadratic formula, the vertex is -b over 2a, and then the function evaluated at -b over 2a. So this is my x coordinate and my y coordinate. So x is going to be equal to -b over 2a. So when we compare this function to our standard form, we have the opposite of negative 6 all over 2 times a negative 1. So that's 6 over a negative 2, so that's going to be negative 3. Then y is the function evaluated at negative b over 2a. Well, since negative b over 2a is negative 3, that means we're going to take the function and evaluate it at negative 3. So we're going to plug in negative 3 into our function up here. So we're going to have the opposite of negative 3 squared minus 6 times a negative 3 minus 4. Okay, so negative 3 squared is 9, but that becomes a negative 9. Plus 18 minus 4. Negative 9 plus 18 is a positive 9 minus 4. This equals 5. So that means our vertex, in terms of xy, is negative 3, 5. Alright, so we know the parabola opens down. We know that our vertex is negative 3, 5. Next question, what is the line of symmetry? Now, you could answer this next question after you graph, but we know that the line or axis of symmetry is x is equal to the negative b over 2a, the x coordinate of the vertex. So that means x is going to be equal to a negative 3. There is our axis symmetry. What is the range? So to answer that question, let's just go ahead and get to the graph. So we'll come back to D. Now what's not added in there is domain, so I'm just going to go ahead and add domain and range. We're going to find those, but let's take a look at our graph real quick first. So again, on your exam, you're going to have a coordinate plane. There's not going to be, you're going to get to define for yourself where you want to plot things. I'm just going to use my grid lines that I have here on my iPad to do this. So let's start off by plotting negative 3, 5. 1, 2, negative 3. And then I'll go up here to 5. 1, 2, 3, 4, 5. Plot that point. There we go. Now, on the exam, what I'm about to do next may not actually be necessary, because when I look at the graph, I'm going to be asking myself questions like this. Do you have the correct vertex plotted, and is your graph opening down? That's really all I'm going to be looking at. So, I mean, honestly, you could take your graph and do this, and I would call that good. Okay, I'm going to take it I'm going to take it one step further. I'm going to do this idea of, remember we talked about the structure of parabolas? This idea that if you go over one, however far you go over, you square that to go up or down. So if I go over 1, I'm going to square that, so I'm going to go down 1. If I go over 2, I square that, I go down 4. So here we go. Down 1, or to the right, left 1, down 1, to the right 1, down 1, to the left 2, down 4, to the left 2, down 4, to the left 3, down 9. So, I mean, I'm going a little bit above and beyond, but if I go down 9, that's going to take me all the way down here to negative 4, negative 4. Which, that lines up with, this starts lining up with our function, because something that wasn't asked here, but I'm going to go ahead and point it out. the constant is your y-intercept. And look at this, just by doing the structure of the parabola, we see that the graph is indeed crossing at -4. Alright, so again, a little bit above and beyond for what I'm going to be looking for. But there we go, there's the graph. So that answers part E. Now, what about the domain and range? So as a recall this, domain is a set of x values. What x values are represented on this graph? Well, according to this graph, I can plug in any x value I want, so my domain is from -infinity to infinity. And range is a set of y values. Now, when we talk about range, this graph keeps going down. It's always going to go down and down and down. But this graph has a cap to it. It doesn't go above this point right here. So my range from least to greatest goes from -infinity all the way up to 5. So when we write this down, we always write from least to greatest. We have from -infinity all the way up to 5, and we put a bracket around the 5 because y is definitely included in our output values for this function. Alright, so does that address your question about problem number 46?
Yes, sir. Thank you.
You're very welcome. Alright, what else can we look at? Anything?
Can we do 47?
Did you say 47?
Yes.
Sure. So, ultimately want to get a sketch of this graph. So, the nice thing about this function is that it has already been factored for us. Check. It's already been factored. And so, to find those zeros, aka the x-intercepts, what we want to do is we want to set each factor equal to 0 and then solve. So I have, when I just look at this, I have 1, 2, 3 factors. So x equal to 0. Well, there's nothing to do to solve here, so we get x is equal to 0. We have this x minus 2 quantity squared. Now, do a little bit of work here, but you're going to realize that x is equal to 2. And then you have the x plus 1 quantity squared equals 0. Do a little bit of work, and you realize that x is equal to a negative 1. Now, one of the things that we've talked about is multiplicity. A nice way to talk about multiplicity, sometimes we say how many times is a 0 repeated. Another way to say this is how many times a 0 occurs. That might be a better way to put it. How many times does a 0 occur? Well, this 0 at x equals 0 occurs once. Now, this 0 at 2 actually occurs twice. And there's a reason why it occurs twice. It's because if you look at it for what it is, you have x minus 2 times x minus 2 equals 0, which gives you x is equal to 2 and x is equal to 2. That 0 at 2 occurs twice. So it has a multiplicity of 2. And we can say the same thing about this 0 at negative 1. It has a multiplicity of 2. Now, when it comes to multiplicity, we interpret this as a behavior of the graph at the x-axis. So if the multiplicity is odd, that means we're going to cross the x-axis, and if it is even, we're going to bounce. So here we can determine that the graph is going to cross the x-axis. Here it's going to bounce, and here it's going to bounce. Alright, so if I just start to plot some information here, I have x-intercept at 0, x-intercept at 2, and an x-intercept at negative 1. Alright, now, I gotta get a sketch of this graph. Now, one way to do this would be to plot some points. So, just going back and doing some real quick work, if I do f at something that's easy to plug in, like negative 10. F at negative 10. So we have negative 10. So I'm just going to write that as negative 10 times negative 10 minus 2, so that's going to be negative 12 squared. And then negative 10 plus 1 is going to be a negative 9 squared. Now, I don't even care about evaluating this. I have a negative times, this is going to be positive, times a positive equals a negative. You know what that tells me? That tells me at negative 10, my function is negative. So, I know, and like I said, I don't even care what that value is. I know that over here, way out here at negative 10, the graph is below the x-axis. Now, since these are my only x-intercepts, I mean, the graph can't come up here and then cross like this. It's below the x-axis, so I know that the graph is below the x-axis. Now, let's start connecting the dots. At negative 1, the graph bounces. So really, the graph would do something more like this. going to come up here and it's going to bounce. Now, you can see what has to happen. It has to interact with this x-intercept, which is also a y-intercept. Why is it also a y-intercept? Because if you have an x-intercept at 0, you also have a y-intercept at 0. So, I'm just going to make it come back up. Now, what does it do at 0? At 0, it's going to cross, so it's got to cross there. Now, it has to come back down to interact with this intercept at 2. What does the graph do at 2? It's going to bounce. So, honestly, I mean, you could go through and do f at 1 to find out how far it goes up. Just look at this graph, or we can do it real quickly. F at 1. 1 minus 2 is negative 1. Negative 1 squared is 1. So you have 1 times 1 is 1. 1 plus 2 is 2. 2 squared is 4. So 1 times 4 is 4. So 1, 2, 3, 4. It's going to go all the way up here to 4. And it has to come back down. And what's it going to do at 2? It's going to bounce. So it comes back down, it bounces, and then it goes back up. And there's your graph. Now, just to clarify, one of the things that I'm going to say in the instructions is to make sure to clearly define your points. So, can I tell from this graph that my points are at negative 1, 0, and 2? Yes. It might be a good idea to label these negative 1, 0, 0, 0, and then 2, 0. But you could, just so that everybody's clear, your graph could look like this. Boom, boom, boom. If your graph looked like that, I would count it correct. And here's why. Number 1, I can tell that's touching at negative 1, it's going through 0, and it's touching at 2. Your end behavior is correct. It's bouncing, crossing, it's coming up, it's coming back down. I would count that correct. Is this a better graph? Yeah, because we took a little bit more time to figure out what's happening at 1, but I would count this correct. All right. Look, we got 8 more minutes. What else can we talk about?
Can we do 59?
59. Sure. Use a calculator to make decimal approximations where necessary, round to 3 decimal places. Alright. So I talked about this problem the other day in one of my classes, and I'll do it again here. Ideally, the ideal thing here is to recognize that we could rewrite with the same base. That's the key thing that's happening here. Recognizing that I can write the left-hand side and the right-hand side with the same base. We should be recognizing that 27 is equivalent to 3 to the third, and 1/3 is equivalent to 3 to the negative 1. That's what the goal is here, is to recognize, oh, I can rewrite the 27 and 1/3 both with a base of 3. So then this becomes 3 to the third raised to the x equals 3 to the negative 1. which then we can use our power rule for exponents to rewrite this as 3 to the 3x is equal to 3 to the negative 1. And then we use this idea, this concept that says that if you have b to the a is equal to b to the c, notice that we have the same base on both sides, there's no other coefficients, then a is equal to c. The exponents must be equal to each other. So we can then say that 3x has to be equal to negative 1, and then with a little bit of work we recognize that x is equal to a negative 1/3. And there we go. Now, let's just suppose I gave you this problem or a problem very much like it, and I gave you the exact same instructions that are on the review. Another way to solve this, so alternate approach, we have the 27x is equal to a 1/3. What you could do is you could do the natural log on both sides. Now, what does this do for us? Well, the natural log, if you take the natural log on both sides, this is going to allow us to use the power rule for logarithms and bring that x out now as a coefficient. Which then you could say that x is now equal to the natural log of 1/3 divided by the natural log of 27. And if you put that answer, I would have to count that correct. I would have to count that correct because that is this. Now, I like this answer better because it doesn't require me to use a calculator to find it. Make decimal approximations. So part of this would be to make a decimal approximation. So if you take
Your conference is scheduled to end in 2 minutes.
If you take your calculator out, you're going to do the natural log of 1/3, close your parentheses, divided by the natural log of 27, close your parentheses, and your calculator, most likely, unless you have it set up to give you rational expressions, is going to give you a negative 0.3333 repeating. That's what it's going to give you. And we need to be recognizing that 0.33333 repeating is a negative 1/3. All right. Well, that's all the time that we have for today. If you have, remember, the review is a good review, but you also have all the exams to go back and look at, because anything that we've talked about, anything that's been on homework, exam, quiz, could be on the final exam. If you have any questions, you can always email me. Our exam is on Wednesday. I'm actually going to be here on Monday. I don't know if the ITB system is going to connect, but I got some I scheduled some exam times on Monday in this room, so I'm going to be here on Monday. I don't know if things are going to connect, but if I'm here, I may be able to help you.
Your conference is now over. Goodbye.
If I don't see you, have a wonderful rest of the semester. Good luck on the exam. Thank you for being my students this semester. Bye.